Hi, and welcome to this last video on principal component analysis. So in the previous videos, we basically derived the PCA algorithm. So in this one here, we're just gonna see or discuss some practical issues that you should be aware of when using PCA. So let us first just remind ourselves what we saw in the previous videos. So when we want to do principal component analysis, was basically a dimensionality reduction method. What we should do is if we have our data matrix X, when we compute the matrix X transpose X, then from this matrix, we find the k eigenvectors set 1 to set k corresponding to the k largest eigenvalues. And then if we wanted to do dimensionality reduction, we could project all of our feature vectors onto the subspace spanned by set 1 to set k. And the way we would do this is just to sum overall set 1 to set k, compute the inner product between x and zi, and multiply with zi. And what we proved in the previous video was that this choice of set 1 to set k actually minimizes the squared loss of the projections, meaning that if you sum over all the samples, x1 to xn, then the sum of the squared distance or difference between the original sample vectors and the projections, this is minimized. And this, we argue that this choice of set 1 to set k, so if you choose among all sets of unit vectors that are orthogonal, then this is the best possible choice to choose these k eigenvectors corresponding to the largest eigenvalues. And if we wanted to, reduce the number of features, we could write x in this basis by just writing the vector that has one entry for each of these k vectors in the basis that just contains the corresponding coefficient if we write it as a linear combination over the basis vectors. Right, so this is all what we saw in the previous videos. Okay, so here's just an example if you try to do this on the MNIST dataset, right? So remember here, these are 724 pixel images, grayscale images, so they have 724 features, each describing the brightness of a pixel. Now, if you actually run this PCA on this dataset, then what we have over here on the left is the eigenvectors corresponding to the top 49 eigenvalues of X transpose X. Right? So we take this whole data set of handwritten digits, and then we compute the matrix X transpose X, and we look for the top eigenvectors. And we'll see all these here, and you can see that in some sense, right, they are, when you compute the inner product between a vector like this one, the 5 here, and one of these vectors in the basis, the more they look alike, the larger the inner product will be. Right. So what this means is that, well, if something over here is shaped like a 5, for instance, like the fourth of these eigenvectors, this is going to have a large inner product onto 5. Now, what we can try and do is we try to look what happens as I add more and more vectors to my PCA basis, right? So increase my k. And what we can see here is that this is the first image is if I only use the first eigenvector here. This is if I use the first 2, the first 3. So still it looks nothing like a 5. Then if I use the first 4 of these eigenvectors, actually it starts looking like my 5 here. And then I can keep adding more and more of these basis vectors, so I keep more and more dimensions in my PCA. And already here, after 18, using the top 18 eigenvectors, what I get is actually a very close resemblance of the original image, right? So it seems that actually I only need to keep 18 coordinates, the projection onto these basis vectors, to actually allow a very good reconstruction of the image. And you would think that it would also be easy to learn from this representation as well, right? It looks very much like the original image. Okay, so right, so in PCA again, right, we use these eigenvectors corresponding to the largest eigenvalues of X transpose X. This is there's something important here that we have to be aware of. In particular, the eigenvectors of this matrix are affected by scalings of the matrix. So let's try and have a closer look at this. Right, so this is just what PCA is. Now, let's say that I have my data matrix, and now let's say I scale up the jth feature by some factor c, right? So I just, for all my data samples, I increase them all, the jth feature by the same factor c. In some sense, right, this shouldn't be important for learning anything, but let's try to see what happens if we scale this jth feature. Now, right, we have to compute eigenvectors of X transpose X. So let's see what happens to X transpose X as I scale the jth feature. Right, so X transpose X, right? So this is basically in X transpose, this is scaling the jth row, and in X, I'm scaling the jth column, which means that in this product, the jth row and the product are scaled by C, all the entries there. The jth column of the product is scaled by C, and this diagonal in entry j comma j is actually scaled by a C squared. Okay. Now, intuitively now, if we let C grow towards infinity, like have a larger and larger scaling, then this one diagonal entry is going to dominate the whole matrix, right? Because it grows as C squared, and the row and the column grow as C, and the rest just stay fixed. So intuitively, right, if we look at it as C just grows larger and larger, then what we have is that this X transpose X matrix, it's basically going to look like a C squared times, well, a matrix that has a 1 in entry J, comma J, and then a 0 everywhere else, right? Because if we look at this matrix here, right, the column would have a 1 over C squared, and the off column and off row will have a 1 over C squared. The row and the column would have a 1 over C. Only this entry in the middle have a 1. So everything else really goes to 0 as C tends to infinity if I move the C squared out. So in some sense, right, this X transpose X is going to look like this, like a C squared times a matrix that has a 1 in entry J, comma J, and 0 everywhere else. Now, this intuitively means that now that what happens if I multiply with the vector Ej, so the Ej is the jth standard unit vector, so it has a 1 in entry J and 0 everywhere else. So what happens is that this product just becomes the jth column of X transpose X, right? So the jth column is just this vector here where, well, basically the jth entry is a 1 and everything else is 0, at least with C goes to infinity. So basically what it's going to look like is basically C squared times Ej. Now, what this means is I have a vector Ej. If I multiply it onto the matrix, it becomes the vector itself times a big scaling. So intuitively, right, it means that we have an eigenvector Ej with an eigenvalue that's C squared, right? And if I let C grow, and it's something, right, it basically means that this set 1, the largest eigenvalue is going to look like C squared, and the corresponding eigenvector will be Ej. So what it means is I will basically have the first vector just be Ej. Now, what happens is now that if we do the projection, if you look at this expression here, like, so what happens is that each of these terms in the sum, one of them corresponds to set 1, which is Ej. So I compute X's inner product onto Ej. That is just the jth coordinate of X, and then I multiply it with Ej. So that basically just means I keep the jth coordinate. Now, more importantly, like all the other eigenvectors here, set 2 to set k, they are orthogonal just by definition of these eigenvectors. They will be orthogonal, which means since set 1, if it is just exactly Ej, it's a 1 in this entry Ej. And if everyone else have to be orthogonal to it, they have to be 0 in that coordinate, right? So all of this means that the only contribution to the jth entry of this projected vector is just keeping the jth entry when I project onto Ej. So said briefly, what will happen is that if one of these features is just much bigger than all the other ones, then basically I'm just going to keep that feature as it is, in particular in the limit as this feature becomes bigger and bigger than all the other ones. So, and this actually happens quite naturally in many types of data. So for instance, consider if the data that you're collecting, your data set consists of houses, and you measure different properties of the houses. You have a feature correspond to the price, maybe one correspond to the number of bedrooms, one correspond to the number of square meters, and so forth. And if you can see here, right, the price basically consists of much bigger numbers than the number of bedrooms and the square meters, which means if you try to do PCA here, what will happen is that the price is just going to be all that you keep, right? That's going to be the first thing that you choose to keep. So you're just going to keep the price as it is. So for this reason, because that might not be what you're interested in doing, what you typically do when you use PCA, not always, but typically, you'll start by scaling all of your features, first of all, so that the mean, which is just the average over all the points value for the jth coordinate, is just going to be 0. And then the variance of that coordinate, so this is now the average over all the points of the square difference between the feature value and the mean in that column, should be 1. Right, so this is a typical, so you kind of normalize the data to make these variances, so the expected square difference from the mean to be 1 and the mean to be 0. And the way you can do this is as follows, right? So let's say you have your data and you start by scaling the features to get a mean of 0. So what you can do is compute the current mean, and then you just subtract that value off from every entry in the column. And it's not too hard to convince yourself that if you do this, then the new mean is exactly going to be 0. Okay, so that's a very simple pre-processing step. Just take every feature, compute the mean in the column, and subtract that off from all the entries. Now, for the variance, we assume that we have already made the mean 0. We have already subtracted off this previous mean to make the mean 0. Now, the variance, again, by definition, is the sum or the average over all the training examples of the squared difference from the mean. Now, the mean we just normalized to 0, so now it's just an average over all the training examples of the square of that feature value. Now, what we do is we just need to make this whole expression become 1 by scaling each of the xij's by the same value. And what you can see is if you move this around, the scaling that you should use is the sigma j, that is the 1 over the square root of the current variance, like the sum of the squares with an averaging. Because then if you plug that in, you replace each xij by sigma j xij, then if you just plug in this definition of sigma j, you'll see that this whole expression just becomes 1. Right, so this is a procedure for then making the variance 1 after you've already set the mean to be 0. Okay, so this is now like a more general PCA. So you do some pre-processing first. So what you do is you start by computing the mean in every data column and then just subtracting that off from every element, every feature value for each of your training examples. And then afterwards, you compute the variance in the column, and you now scale all the entries by 1 over the square root of this current variance that you had in the beginning. And then you've pre-processed your data. Now it's ready for PCA. Now all of the columns have kind of the same magnitude. And so now you compute these k eigenvectors corresponding to the k largest eigenvalues of x transpose x. You can project if you want. And maybe one important thing is that, well, if you just want to write all your training data in this basis, recall that if you want to write x in this basis, the projection of x in the basis, set 1 to set k, then it's just the vector of all these inner products. And if you can see that this is what I get if I take x and multiply it with set, then because the set here with these column vectors having all the set 1 to set k's, and if we compute this product here, I basically get that each of the feature vectors are each of the rows here. I just multiply it onto the sets, and you get a vector with each of the new rows are just these projected points. So also you can see here, this is an n by d matrix with a d by k. So the product is an n by k matrix. Okay, so now that you have reduced the dimensionality of your input, now you have a new data matrix here, right? That's an n by k. And then what you can do is you can just plug this into all these ML learning algorithms that we've already seen previously in the course, right? Support vector machines, maybe linear regression, logistic regression, and so on, right? You can just use any of them with a new data matrix that only have k features and not d features, right? And now finally, if you do this, right, the important point is that if I get a new training example, just for instance, a new house that I've gathered information about, then the important thing is that we actually have to apply the same, say, scalings and updates to the features before we plug them in and try to use them with these models that we trained on the data X set. At some point, we have to do the same transformation to this feature vector X. So basically, we subtract off first the mu j from the jth coordinate. So we have to store these mu j's. And then we have to scale the jth coordinate by the sigma j. So we also have to store those. And then we have to project X onto this subspace as well, right? So it also becomes k-dimensional. So you can actually use it together with whatever model you trained. And this is just done by taking X transpose and multiplying it with set. And then we have just the k features, right? So this is basically just applying the same scaling that you just computed and the scaling that you applied to the data that you had for training, for computing the PCA. Okay, so this is just an important point to keep in mind. Okay, so maybe one thing that's worth mentioning here, just as a sanity check, is that when we reduce the variance and set the mean to 0, and one important thing is that only the directions of the standard unit vectors actually have variance 1. So why is this important? Let me try to explain. So first of all, right, the first transformation we did to the data was to make the mean 0. And then once the mean was 0, we set the variance to be 1. So we kind of shrink it in the X and Y direction and scale it in the right way so that the variance is also 1. And the variance now is, the important thing is the variance is 1 for the original features, right? So the variance is 1 in the X direction here. The variance is 1 in the Y direction here. Now, remember again, the definition of PCA, one of the motivations was that we choose the directions of maximum variance, right? Those are the set 1 to set k that we find. And now let's assume that, if the variance was 1 in every single direction, then we wouldn't be computing anything interesting, because we might as well have stayed with the original feature vectors, basically all the standard unit vectors as our representation, our basis. So it's actually important here that the variance can actually be bigger than 1 in other directions, right? So it's still sensible to use PCA. So maybe that's an important point just to have in mind, that it still makes sense to compute PCA, even though we kind of made the variance 1, but only in the directions of the original features, the standard unit vectors. Those are the only places where the variance is 1. Okay. Right, so still meaningful. And right, so the algorithm again was like compute these top k eigenvectors for x transpose x. And let me just say there are many different algorithms for computing them, and there are many efficient ones that you can find in most libraries as well, right? So there you can just use a singular value decomposition of x and so on. There are many different choices. And also PCA is actually already implemented in most learning software libraries. Okay. So let's just remind us of just a few more comments before we wrap up. So we chose these vectors Z1 to Zk to be the directions of largest variance, right? So for instance, remember this initial picture where we didn't normalize the data yet, but the intuition was that we chose this direction Z1 because the data basically has the most variance, so the Z1 direction explains the most about the data. That was the intuition that we started out with. We would like to choose these directions of largest variance. And what we did in most of these previous videos was to use PCA to do dimensionality reduction, to reduce the number of features to just k, to find a smaller representation and speed up computation, perhaps. But actually, sometimes in practice, just knowing what Z1 to Zk is a goal in itself, right? Because maybe these directions say something interesting about the experimental data. If you look at what is this linear combination, what are these vectors, like these directions? They say something, right? They give you the direction of largest variance. Maybe this is somehow an interesting measure for experimental data that you've obtained. So it's just a note that sometimes you just obtaining the Z1 to Zk can be a goal in itself. Right. So let us end here, right? Just with this nice picture that PCA applied to the MNIST dataset already, with just 18 feature vectors, 18 basis vectors Z1 to Z18 corresponding to the top 18 eigenvectors. You get a very nice reconstruction of, for instance, this image 5.